Good morning, everyone. Now I'm going to present temporal reasoning on large-scale graphs. My name is Hassan Chaudhry, and this work is jointly done with Pietro, Alessandro, and Matteo. Initially, I'm going to motivate the problem, and I'm going to tell you why it is an interesting and important problem. Then we will talk about the proposed architecture. Finally, I will conclude the presentation and take your questions if there are any. Large-scale graphs are very important. They represent interconnected systems and they are found in several areas and domains. Typical examples could be social media graphs such as Facebook, Twitter, LinkedIn, and so on. They are very important in Internet of Things. They are found in other domains like protein-protein interaction graphs, e-commerce, and video portals. We apply different algorithms on these large-scale graphs, and these algorithms reveal important inside information from these graphs. Typical examples can be community detection, page rank, collaborative filtering, and so on. There are a large number of frameworks which allow applying these algorithms on large-scale graphs, and most of them are distributed algorithms. So these frameworks divide or partition the graph onto multiple systems across the network, and then they apply these distributed algorithms to compute different algorithms on these large-scale graphs. Most of these frameworks work for static graphs very well, or graphs which are changing very slowly. So updates in these graphs are very slow or they are almost static. However, modern-day graphs are dynamic and they evolve with time. This continuously updates the structure of the graph. This is a sort of a very challenging scenario for the current graph processing frameworks. And yet more challenging is to find and detect pattern of changes as the graph evolves with time. So traditional graph processing systems do not support such temporal analysis and detection of pattern as the graph evolves with time. Now, one of the very familiar area is complex event recognition. It identifies composite event of interest, and this sort of uses particular pattern to find a collection of certain events. Now, this complex event recognition is a very well-known area. However, it cannot be applied to large-scale graph because these complex event recognition systems use operators which can support a very limited amount of state, while large-scale graphs need a large information. The abstraction for large-scale graphs is mostly iterative in nature, and this is not supported by traditional complex event recognition systems. So InnoCarac's complex event recognition system do not directly support large-scale graphs. However, they give us some information how we can apply these techniques on large-scale graphs. So our aim of this work is basically to integrate large-scale graph processing capabilities along with complex event recognition. Now, this sort of gives you a very high-level view of the idea. So you could see in the center of this slide, there is this large-scale graph, and this large-scale graph receives graph updates from the left corner. Now, as these graph updates come into this large-scale graph, it continuously updates its structure. Along with this updates, we could sort of install a pattern which provides a overlay temporal reasoning on this large-scale graph, and we could find complex events using this temporal reasoning. So this is sort of a basic motivation of the work, and now I will dive into the algorithm itself. So following is the proposed architecture. This work is basically a framework for graph computation along with complex event recognition, and we call it FLOWGRAPH. So we provided a framework called FLOWGRAPH built in Akka in Java, and this framework provides graph computation as well as complex event recognition. So we provide a complete framework and semantics which allows you to detect patterns as the graph evolves with time. Along with that, you can also perform graph computation as part of your pattern. So I will give you a very brief idea, a very high-level overview of this framework without going into too much details due to the shortage of time. So here I'm going to present you a very high-level overview of FLOWGRAPH's language model. So the first thing in FLOWGRAPH pattern is graph computation. This is typically an iterative algorithm, and few examples as given before could be community detection, triangle counting, page rank, and so on. Once this graph computation is processed, is performed, we next extract meaningful information in a form of subgraphs, edges, or vertices. This meaningful subset of graph would later be used to apply and evaluate with a temporal predicate, and this is going to determine if certain temporal pattern exists or not. So this pattern in totality provides you graph computation as well as temporal pattern detection. Now, this framework also provides temporal reasoning, and we support for now two basic types of temporal reasoning. So the first one is a go. It talks about some event which happened t time units before, and we could represent this event in our language. The second type of events are so-called continuously occurring events, and they're represented by every keyword. So these events occur at every t time units within a certain frame of window, and they repeatedly occur. So here is a brief overview of the temporal logics. So the first one, as we already discussed, is a go, which represents a event which occurred t time units before. And the second one is every, which represents something which is happening at regular time intervals within a certain window of time. So finally, I will talk about a flow graph architecture. The flow graph architecture consists of two major pieces, the master and workers. So master, you can see in this slide on the top, is a central piece of this architecture which provide orchestration and management to this entire design. As such, master does not have any piece of graph to process, but it provides load balancing, graph partitioning, fault tolerance, and other management operation to this entire system. While the workers, which are represented by node here, contains a section of graph, each worker or node would have its own partition of graph, and this partition of graph would have graph processing as well as temporal reasoning deployed on it. So all these workers or nodes, they intercommunicate with each other to perform the graph computation as well as to find a certain temporal pattern, and they also communicate with master on regular intervals. That sort of concludes my presentation. This framework is part of my ongoing PhD work, and we are extending this framework, of course, in the future, and we are actually including query optimization as a future work in this framework. Also, we are providing more temporal patterns to find and support interesting applications. Following are the references of this presentation, and you are more than welcome if you have any questions.